Hi, welcome to my class on statistical physics. This is a lecture for my MSc students of Sem 2. We would like to start on with grand canonical ensemble. Now, before we really get into this business of grand canonical ensemble, I would like to give you a bird's eye view of this total ensemble theory, what we have learned till now. Well, in the microcanonical ensemble, we studied with a completely closed system. If I say this is a closed system or isolated system in which the number of the particles or the microstate of the system was defined by the number of the particles, the energy and the volume, and they all were fixed. That means there was no number change, no energy change, and obviously the volume was also no change in volume. For that we need to call this as microcanonical. Okay, microcanonical ensemble. What happened in canonical ensemble? That we do encounter with certain physical systems in which we need to vary the energy. So there you have to this were all zero. For the canonical there was no change, so delta n is equal to 0, delta E is equal to 0 for microcanonical. For canonical ensemble, what we did, we had a variation of energy. And how do we do that? We have the system, this is my system again, and then we have this as the system. Again, here also we have a system in which we have the number of the particles n, the volume, and then the energy can be exchanged with the reservoir. So you have a reservoir where you can have an exchange of energy for that. So here the microstate were defined by NeV, and since you have delta E not equal to 0, there is a wall between the system and the reservoir, which is a diathermic wall. If this wall is diathermic, that is, there is an exchange of energy between the two systems, then what remains constant is the temperature T. So temperature was another parameter which was taken as a fixed thing in the case of canonical ensemble, where there was an exchange of energy. And we have such physical system where there is an exchange of energy, and energy can vary between 0 and infinity, and we can keep another parameter fixed, which is the temperature. Now we would come on to the grand canonical ensemble, which is a kind of more general concept, where so here it was delta E not equal to 0, so here delta N was 0, delta V was 0, but delta E was not equal to 0. How is the volume kept fixed? You fix the walls, fixed walls. How the numbers are fixed? You have an impermeable membrane. Impermeable membrane between system and reservoir. Okay. Now we come to so these are the microcanonical, and now let us try to see grand canonical. What would happen in this particular case? Grand canonical ensemble, we have certain systems where we need to even vary the number of the particles. So if we have a system, this is my system and this is my reservoir. Okay. and since n can be exchanged between the systems and the reservoir, volume is kept fixed, energy can be exchanged. So here delta n is not equal to 0 and delta E is also not equal to 0. So we have a system, but delta V is equal to 0. So for this we need to have a parameter for which delta n is not equal to 0. We define a parameter which is called the chemical potential. So we have chemical potential to be fixed. Here it was temperature which was fixed due to the exchange of energy. Here it is the chemical potential which can be kept as fixed, and for this it is the temperature. So this is chemical potential and temperature. These are the two parameters, rather the three parameters which can be kept fixed or for which we want to see or correlate the thermodynamic system with the statistics are the mu, v and t. Here it was n, v, t. You remember in case of canonical ensemble we defined the partition function which was a function of n, v, t. Here we would define a function similar to that of the partition function, which would be a function of mu, v and t. So you can define here also a function which is a function of mu, v and t. So I hope more or less the concept of the bird's eye view approach to really this ensemble theory is very much clear with this short introduction. Okay, so let us first of all try to define the grand canonical distribution function by means of the equilibrium, the concept which we have used even in canonical distribution, that is the equilibrium between the system and the reservoir. So I am again redrawing my system. This is my system with fixed walls. This is my system. And this is the reservoir, which this is fixed, but this is a semi-permeable membrane which can exchange the number of the particles. V is fixed and energy can also be exchanged. So delta n not equal to 0, delta E not equal to 0, and this is my reservoir. And I want to define three parameters, mu, v, t. This wall are fixed walls, which makes delta v to be equal to 0. There is no change in volume. Now we can always define, let's say there are nr number of particles and es number of energy levels of a system, and there are nr prime of the reservoir and the corresponding energy levels for the reservoir are es prime, such that the total number of particles nr plus nr prime is equal to n0. The total number of particles of the whole of universe, system plus, rather the total number of particles of this whole system plus reservoir, and es plus es prime to be equal to E0, the total energy. This is the total number of particles and this is the total energy. Now if we want to, we can very easily say that then nr by n0, which is equal to 1 minus nr prime by n0 is much less than 1, and similarly es by E0, which is equal to 1 minus es prime by E0 is much less than 1. This condition is necessary in order to define the probability distribution function. So let us define at any time t, if P or S be the probability distribution function, P or S, then this should be proportional to the number of the microstates of the reservoir having energy ES prime. Okay, first of all write NR prime and then ES. NR prime and ES prime. We can write this proportionality only when the number of the particles in comparison to the total number of particles of the system in comparison to the total number of particles is very less than 1 and the energy is of. So we can write the probability of finding a system in a state having NR number of particles and ES energy levels to be proportional to the microstates present in the reservoir in terms of a large number of particles. The larger the number of the particles, the more probable would be the presence of the state, equal a priori probability. Now what is this omega prime? This is the reservoir. This is the microstate for the reservoir. So we can write this as equal to omega prime. NR prime is nothing but equal to N0 minus NR, and ES prime is E0 minus ES. And obviously if we want to write this number of microstates are obviously very large, so we can take log natural of omega prime N0 minus NR and E0 minus ES to be equal to, we can expand this in terms of Taylor series in about N0 and E0, so we can write it as ln of omega prime N0 E0 minus del of ln omega prime by del of n prime at n prime is equal to N0, okay, into n prime minus N0 minus delta of ln omega prime by del of E prime. E prime is equal to E0 into ES prime minus E0 and higher order terms. So we can approximately write this as ln of omega prime N0 E0, and this is nothing but, we can say from our previous knowledge as we studied in our first class when we correlated the microstates, variation of the microstates, log natural microstates per unit number of particles can be defined as the chemical potential by kT. So we can write this as equal to plus of mu prime by kt prime, if mu prime and t prime be the, so we have, let it be mu prime and this be t prime, because prime coordinate are reserved for the reservoir. So mu prime by kt prime, and this would be equal to nr. So n of r minus of nr. So this was minus mu by kt, so this becomes nr, and this becomes minus of 1 by kt prime and es, because E0 minus Es prime is equal to Es, so that would be minus, and this is minus of this is equal to minus of, sorry, I have to write it as plus, okay. So this would be not fine, because this would be minus of mu prime by kt, and we have used the relation del ln omega prime by del n prime to be equal to minus of mu by kt, okay. So mu prime by kt prime. So this is minus mu by kt and this is minus of nr, so that becomes plus, and this is equal to 1 by kt and that is minus of es. So we can write this to be roughly approximately this, and so omega prime can be written as something like omega prime is proportional to e to the power, and if they are in equilibrium and we have the chemical potential to be mu and the corresponding temperature to be T, then we can say in equilibrium condition, equilibrium between system and the reservoir, system and reservoir, we can write T prime to be equal to T and mu prime to be equal to mu. So we can write this to be equal to omega prime to be proportional to some constant, because this is constant, this is the total energy and the total number of particles, and e to the power alpha minus alpha nr and minus beta es, where alpha is minus mu by kt and beta is 1 by kt, okay. And normalizing, if we normalize this, normalized distribution function, we can just jump on to the distribution function, that is PRS, which was proportional probability of finding the system having the number of the particles nr and the energy level Es. Then we can always write this to be equal to this divided by summation over r and s. So this would be equal to e to the power minus of alpha nr minus beta es, and since we are doing a normalization over r and s, so we can write e to the power minus of. So we have arrived at the distribution function, the grand canonical distribution function, which looks like this. This is by using the equilibrium approach between the system and the reservoir.